Welcome. Today, we're going to explore one of the most important equations ever discovered in science, the Schrödinger equation. At first glance, it may look like a complicated mathematical formula, but this equation completely changed the way scientists understand the universe. It became the foundation of quantum mechanics and helped explain how atoms, electrons, and matter behave at the smallest scales. In fact, many modern technologies, including computers, smartphones, lasers, and quantum computers, depend on ideas that ultimately trace back to this equation. But before we understand the equation itself, we first need to understand the mystery it was created to solve. Let's begin our journey into the quantum world.
Before we talk about quantum mechanics, let's think about the everyday world. Imagine throwing a football. Even before it lands, you can roughly predict where it will go a few seconds later. The same is true for planets orbiting the sun. Scientists can predict their positions years and even centuries into the future. These predictions are possible because objects in our everyday world follow well-understood physical laws. For hundreds of years, classical physics helped us explain and predict motion with incredible accuracy. Everything seemed to make sense. But when scientists began studying the tiny world inside atoms, they discovered that nature behaved very differently. And that's where our story begins.
In the late 19th and early 20th centuries, scientists began uncovering the structure of matter. They discovered that everything around us is made of atoms. But atoms were not indivisible, as people once believed. Inside every atom, scientists found even smaller particles, including electrons. This discovery opened the door to an entirely new world. A world so small that it could not be seen directly. At first, physicists assumed that electrons would follow the same rules as larger objects. After all, if planets orbit the sun, perhaps electrons orbit the nucleus in the same way. It seemed like a simple and logical idea. But very soon, scientists realized there was a major problem. The microscopic world was not behaving the way classical physics predicted. And this unexpected mystery would eventually lead to the birth of quantum mechanics. Scientists imagined electrons orbiting the nucleus just as planets orbit the sun. At first, this seemed like a perfect explanation. But there was a problem. According to classical physics, an orbiting electron should constantly lose energy. And if it loses energy, it should gradually spiral inward and crash into the nucleus. If that were true, atoms would collapse almost instantly. But that's not what we observe. Atoms are stable. Everything around us, from the air we breathe to the stars in the sky, is made of stable atoms. So physicists faced a major mystery. Why don't electrons fall into the nucleus? The old laws of physics couldn't provide an answer. And solving this puzzle would eventually lead to one of the greatest revolutions in science. For hundreds of years, classical physics successfully explained the motion of objects, from falling apples to orbiting planets. But when scientists applied the same laws to atoms, the theory stopped working. Electrons simply did not behave the way classical physics predicted. The microscopic world seemed to follow completely different rules. It became clear that understanding atoms would require a new kind of physics, and that new physics would eventually become known as quantum mechanics. In 1924, a young physicist named Louis de Broglie proposed a remarkable idea. What if particles could behave like waves? At first, this sounded strange. After all, particles and waves seem completely different. But de Broglie suggested that matter itself might have wave-like properties. This simple idea would become one of the foundations of quantum mechanics. According to de Broglie's idea, every object has a wavelength. For large objects like footballs, cars, or planets, that wavelength is so tiny that we never notice it. But for very small particles, such as electrons, the wavelength becomes important. This means that electrons can behave like waves instead of tiny solid particles. And this wave-like behavior would soon become the key to understanding the quantum world. One physicist was particularly inspired by this idea. His name was Erwin Schrödinger. He asked a simple question: if particles behave like waves, can we create an equation that describes those waves? In 1926, he found the answer. His work led to one of the most important equations in science and laid the foundation for modern quantum mechanics. In 1926, Schrödinger introduced an equation that would transform physics. Today, we know it as the Schrödinger Equation. Don't worry about the mathematics for now. The important idea is that this equation describes how quantum particles behave over time. Just as Newton's laws predict the motion of planets, the Schrödinger equation predicts the behavior of electrons and other quantum particles. It became the mathematical foundation of quantum mechanics. So, what does the wave function actually tell us? Surprisingly, it does not tell us the exact location of a particle. Instead, it describes all the possible states the particle can be in. In other words, quantum mechanics does not give us certainty. It gives us probabilities. The wave function tells us what might happen and how likely each possibility is. And this idea completely changed how scientists think about reality. At the heart of the Schrödinger equation is a symbol called psi, written as the Greek letter phi. Psi represents something known as the wave function. You can think of the wave function as a mathematical description of a quantum particle. It contains all the information we can know about that particle. Whenever physicists want to predict the behavior of an electron or another quantum object, they begin with the wave function. In many ways, the wave function is the most important idea in quantum mechanics. And understanding what it means is the key to understanding the quantum world. One of the biggest surprises in quantum mechanics is that electrons do not orbit the nucleus like tiny planets orbiting the sun. Instead, they exist in what scientists call a probability cloud. This cloud does not show where the electron is. It shows where the electron is most likely to be found. The darker and denser regions represent a higher probability, while the lighter regions represent a lower probability. So rather than predicting an exact location, quantum mechanics predicts the likelihood of different locations. This is a completely different way of thinking about nature, and one of the key ideas behind the Schrödinger equation. Now we arrive at one of the strangest ideas in quantum mechanics. Before we make a measurement, an electron does not have one definite position. Instead, it exists as a range of possibilities, represented by the probability cloud. The wave function describes all of these possible outcomes. But when we perform a measurement, we observe only one result. One possibility becomes reality. This is why the image shows many possibilities before measurement and one outcome after measurement. In quantum mechanics, observation is not just passive. Measurement itself plays an important role in determining what we actually observe.
One experiment provided some of the strongest evidence for quantum mechanics. It is called the Double-Slit Experiment. In this experiment, particles, such as electrons, are fired toward two narrow slits. If electrons behaved like tiny balls, we would expect two simple bands to appear on the screen. But that's not what happens. Instead, an interference pattern appears, exactly like the pattern produced by waves. This surprising result shows that electrons can behave like waves. The double-slit experiment revealed that the quantum world is far stranger than our everyday experience and became one of the most famous experiments in the history of science.
So what does the Schrödinger equation actually allow us to predict? The answer is the behavior of atoms. Using this equation, scientists can calculate how electrons are arranged around the nucleus and why atoms remain stable. It also helps explain why atoms combine to form molecules and chemical bonds. The equation can even predict the unique light patterns produced by different elements, which is why it is important in spectroscopy. And by understanding how electrons behave inside materials, scientists can explain many electrical, magnetic, and optical properties. In short, the Schrödinger equation helps us understand the microscopic world and the building blocks of matter itself.
The Schrödinger equation is considered one of the most powerful equations in science for a simple reason. It allows us to make incredibly accurate predictions about the quantum world. From atoms and molecules to complex materials, its predictions match experiments with remarkable precision. It helps explain chemistry, physics, and many properties of matter using a single mathematical framework. Even today, nearly a century after it was discovered, scientists continue to use it in research and technology. In many ways, the Schrödinger equation is not just an equation. It is a tool that helps us understand nature at its deepest level.
Quantum mechanics is not just a theory found in textbooks. It is part of the technology we use every day. Computer chips, lasers, and smartphones all rely on quantum principles. Even the emerging field of quantum computing is built on the ideas of quantum mechanics. So, while the Schrödinger equation was created to understand atoms, its impact extends far beyond the laboratory. From tiny particles to modern technology, quantum mechanics helps power the world around us.
Let's take a moment to reflect on what we've learned. We started with a simple question. How do we describe the behavior of tiny particles? Along the way, we discovered that particles can behave like waves. We learned that quantum mechanics predicts probabilities rather than certainties. We saw how measurement can affect what we observe. And we explored the famous double-slit experiment, which revealed the strange wave-like nature of matter. All of these ideas come together in the Schrödinger equation, a single equation that helps us describe and predict the behavior of the quantum world. Quantum mechanics may seem strange, but it has transformed our understanding of reality and helped create the technology we use every day. And it all begins with the Schrödinger equation. Thank you for watching, and I'll see you in the next video.